In this video, we are going to continue from where we left off in the last video. We're going to talk about communication between the threads. Like I explained towards the end of the last video, we have two different approaches when it comes to communication between threads. One is where we use a shared state to communicate. The other technique is message passing, where we communicate to share state. In today's video, we're going to focus on the first approach, where we use a shared state to communicate. This might look like a single approach, but there are several different variations when we prefer to go with this approach. So we're going to cover all the concepts and all the patterns that fit in this approach. Before we get to the code, I want to explain the key issues, the key challenges when we work in this approach. If you are watching this video, you must already know that a Rust compiler is quite strict when it comes to ownership of the variables. Even when you use a single thread, there can only be a single mutable reference for any variable, right? Then how do we allow the state to be able to be mutated by multiple threads? So how do we pass ownership? That is the first challenge. And the second challenge is, how do we dictate the terms of interaction with the state? So what I mean by terms of interaction is, at what frequency is the data going to be read or written by these threads? So how does Rust allow you to tackle these two challenges? Rust offers something called concurrency primitives that allow you to overcome these two challenges. Again, everything that I'm explaining in this video is already part of the standard library. So if you have time, I would suggest you to go to the standard crate and read through the sync module and also the thread module, especially the sync module, because that holds the information related to communication between the threads using the shared state. So like I said, Rust offers something called concurrency primitives to tackle these two issues. So we have two kinds of concurrency primitives. One is ownership primitive. Like I said, when you're passing data between the threads, you need to also safely transfer ownership. So we have a thread safe ownership primitive to handle that. And the other primitive is to handle the interaction with the state. So for that, we have synchronization primitives. So let's take a look at that. So the way this works is, whenever you have a shared state, you need to wrap your state in this primitive. So the first, you wrap your state into a thread safe ownership primitive. That way, whenever your threads are accessing the data, the ownership primitive will handle the ownership side of the things for you. Next, you need to wrap your data in a synchronization primitive to dictate the terms of interaction. So the synchronization primitives will serialize or coordinate the interactions between the threads while accessing the state. Okay. This thread safe ownership primitive is called arc. Again, we'll look at what methods are inside arc a bit later when we get into the code. So we use arc to handle the ownership side of things. And then we have mutex, read write log, and several other synchronization primitives, which we'll get to shortly. So this is how the pattern works. So whatever state you want to share between the threads, you mutate them in these two primitives. First, a thread safe ownership primitive, which is arc, and then a synchronization primitive, which is mutex or read write log, or some of the other ones which we'll look into shortly. We're going to use the same code base that we used in the last video. I'm going to create a new folder to create the demos for this video, but let's do some cleanup before we get there. I'm going to create a new folder called basics, and I'm going to move all the previous demos into the basics folder. Then I'm going to create a mod file. Then I'm going to export everything via the mod file inside the basics folder. And in the main folder, instead of directly accessing the demo file, we're going to access the basics folder. So that's it. So here you can test out the basics without breaking anything. So you can use everything inside the basics folder, and if you want to run any demo, you can go to that particular demo and run the demo function. So this retains the code that we built in the last video. Now I'm going to create a new folder called shared state. And here is where we're going to have the demos for this video. Okay. Before we get there, I want to show you a UML diagram that I created to capture everything that we discussed in this video. So let me do a preview of that file. Let's close this. Let's also close this. All right, here is a preview of the file. So again, we are discussing about thread communication, and there are two different techniques, shared state and message passing. We're going to focus on the shared state, and within this, first we need to understand the primitives. like I said, there are two kinds of primitives: thread safe ownership primitive, which is arc, and then we have synchronization primitives, which is mutex, read write lock, atomic use size, barrier, conditional variant, and once lock. Again, these it might look like I'm throwing a lot of jargons at you, but we'll cover all of these in this video. And finally, these are the different methods, key important methods that we need to understand for each primitive. Okay, and these are the different patterns that we implement in this video. I'll explain this when we get to that particular pattern. Okay, in the shared state folder, I'm going to create a mod file and also demo1.rs. Inside demo1.rs, I'm going to create a function, public function called demo, and in the main file, I'm going to import this module, shared state, and use everything inside shared state. And to run the demo, I'm going to say shared state demo1 demo. That's it. Okay, that completes the boilerplate setup. Let's look at the examples now. The first pattern that we're going to look at is many writers, which is a pattern that you want to use when you have multiple threads writing to the same state. In this case, you want to wrap your data in first the arc primitive to safely handle ownership between the threads, and then we're going to use the mutex primitive, which is going to lock every time the data is being accessed. Okay, let me show you the demo. Instead of writing each and every single line of code, what I think would be better is to finish the boilerplate, the basic set of code, and then shed light on the important lines of code, so that I can condense this video while still providing valuable information. Okay, so I'm going to set up a basic thread and then implement the arc, and then we'll get to the arc and mutex side of things. Okay, so first I'm going to import spawn function from the thread module. Then I'm going to create a state, a string state that we want to share between the threads. Then I'm going to create a handles vector where we're going to store all the handlers. Again, I covered these in detail in my basics video, which I would suggest you to watch before watching this video. Then I'm going to create a handle where we're going to mutate the string and push that handler to the handlers vector. Then finally, we're just going to use join function to wait for these handles to complete. Okay, let's hit save. So far so good. We didn't run into any issue. See what happens when you add a new handler. So as soon as I add a new handler and hit save, we get this error: use of moved value, state value used here after the move. So what this means is the state that we want to share between the threads is already, the ownership of the state is already transferred to this thread by this handler. So you cannot reuse it again in this handler, right? So this is why you need to wrap your data inside primitives to avoid causing these errors. Alright, I imported the arc function from the sync module. Now we need to wrap your state inside this arc primitive. So we can do that using arc ;new. So you can use a new function to wrap your data. This initializes the arc. Arc stands for atomic reference counter. So the way this works is every time you access the state inside the arc, the counter increases by 1 and shares ownership, and it keeps tracks of all the shared ownerships using that counter. Okay, and first here we're going to get a shared reference. We can use the clone function to get the shared reference, and then I'm going to create a handler and push the handler to the handles vector, and do the same for the second thread, and let's hit save. Now let's see what error we get. So we cannot borrow arc in a mutable trait. So this is the second error we get. So arc only handles the ownership side of things. We need to use a synchronization primitive along with the ownership primitive to be able to properly mutate the state. So let's import mutex, and so here along with arc, I'm also importing mutex, and let's wrap the state inside the mutex primitive as well. Then inside the spawn function, we can get the borrowed state using the log function. Okay, and then we can just make the changes to the state using the borrowed state. Okay, and finally I'm just going to log the borrowed state here. Let's hit save. Now we can see all the errors have disappeared. Let's do the same for the second thread as well. Alright, we did the same for the second thread, and now we can see we don't have any more errors. So we have two threads mutating the same state, which is possible because of, again, mutex, which is a synchronization primitive, and arc, which is the ownership primitive. Okay, so let's run this, and as you can see, it works fine and the string was mutated twice, once from the first thread and second time from the second thread. Okay, I could end this topic here, but I want to give you a few more examples with arc and mutex, because this is one such pattern that I believe is used very often, and even on YouTube you'll find a lot of videos on arc mutex. So I want to cover a few more scenarios. Instead of using a plain string, why not do something with numbers? Okay, so I'm just going to comment out this code so that you can access it. It's available for you when you want it, and create a new function. Okay, in this demo what I want to do is I'll create a U32 state, and I'm going to mutate that state from two different threads. And what I specifically want to show you is how the thread has to wait when the other thread is mutating the data, and vice versa, so that you can see when the thread is waiting, how does it look at the log level, and and when it's available to be mutated, how that looks again at the log level. So we'll have a few logs, and I'll show you how when the lock is imposed by one thread, the data becomes inaccessible for the other thread. Okay, let's create a state of U32 value with initial value of 0 and wrap it in arc and mutex primitives. Then I'm going to create handles to store all the handles, and then I'm going to create reader state. I'm going to acquire reader state. In this reader state, I'm just going to view the data and log it. Okay, so inside this reader state, I'm going to define the function where we're just going to loop 20 times, and inside each loop we'll just to acquire the lock using the try-log method. And if we acquire the lock, we just print the current state of the guard, the state. And then if we don't get log access, then we're going to log that the log is busy, and we'll retry. And if there is an error, then with the mutex, then we're just going to log that as well. And finally we're just going to wait for 80 milliseconds so that each loop has some padding, and we don't just keep continually trying to acquire the lock. And then finally just push this handler to the handles vector, and then we're going to acquire the write state using the arc clone. And then we're going to create a writer handler where we just wait for 200 milliseconds, and after that we're just going to acquire the lock and mutate the value to 10, just increase the value to 10, and then just write that to the log and just release the log after 120 milliseconds. Okay, let's hit save. Finally, just push the writer and just join these handles to just wait for these threads to execute. Just make sure that you set these wait times appropriately, otherwise the write log will not be able to acquire access properly. Okay, so in this case the read log is incrementing by 80, right? So 200 is not a multiple of 80, so there shouldn't be any conflict. So let's run this and see what we get. Awesome. So when we start the program, you can see the value was 0. The reader thread is logging the current state to the console, and once the writer acquires access, you can see that the reader was busy. Your reader could not acquire the lock access because the writer was mutating the value. And finally, after the writer released the log, the reader was able to gain back access, and the current state is 10. This is how we can use arc and mutex to share the state between the threads, and use this pattern when you have a lot of threads writing to the same state. Okay, I'm going to rename this file to many writers, and also update that, save, and also update that in the main.rs file. Yes, hit save. Perfect. Although this is a good example, this is not the case when you would use a mutex. A mutex is recommended when you have multiple writers, right? In this example, we just demonstrated a single reader and a single writer. So let's change this demo slightly and have multiple readers. So I'm going to have 4 readers, and four writers, and each writer is going to loop 3 times and try to mutate the value. Okay, and each writer is going to have 3 steps, and we're going to log which writer and at which step mutated the state. Okay, and we're going to set the wait times appropriately, the sleep times appropriately, so that there is no conflict between the threads. And yeah, let's run this. can see the final state is 12 because we have 4 threads mutating 3 times, incrementing by 3 times, so 4 3s are 12. So first, the reader saw the state 0, and then writer 0 at step 0 mutated to state 1, and so on and so forth. That's about it. I'll save this and let's move on to the next pattern. In our UML file, I'm also going to highlight the concepts that are covered in this topic. So we have looked at arg, and we also looked at both the methods new and clone. So I'm going to highlight those in green boxes. And also the mutex, we have tried new, log, and also try log inside the reader handler. And I'm also going to highlight the many writers pattern. Okay, I'm just marking these as completed topics. Next pattern that we're going to look at is many readers pattern. And many readers is a pattern that's recommended when you have a lot of threads which are competing to read the state, whereas you only have a few threads that occasionally write the state. Okay, and the sync primitive recommended for this is rwlog, which is read write log. And these are different key methods that you want to master if you want to implement this pattern. Okay, I'm going to create a new file called manyreaders.rs and create a simple demo function which is going to be public. I'm going to export this from the mod file, and in the main.rs file I'm going to run this demo instead of the many writers. That's it. Alright, in this demo, first I'm going to create the shared text, and instead of mutex, I'm going to use the rwlog, the sync primitive. We still need to use the r primitive to handle ownership, and we're going to look at different methods that are offered by rwlog, which is new, read, write, and try read and try write. We're going to explore these methods inside the rwlog sync primitive. So first I'm going to create a shared state from the string hello, and then I'm going to create handles. And let's look at the first example, which is read, right? Accessing data with the read. So first I'm going to use rclone to extract ownership in the read log, and then I'm going to define the handler function, and inside that I'm going to loop 4 times. And can you call the read function to gain the read access? And for now we can just log the value, and then you can just wait between each iteration for around 90 milliseconds and just finally push that handler to the handles vector. So let's run this and see what we get. Awesome. So for each iteration we saw the current value of the state. Okay, we haven't mutated yet, but let's look at the second method. In this second method we're going to use try read instead of read, which is non-blocking. And as always, first we'll try to gain ownership using the rclone, and then we'll define the thread function, and inside this function we're going to loop 12 times, and each time we're going to call try read, and it's going to have return multiple. We need to handle all the cases using the match operator. So whenever we acquire the lock, we're just going to log the value, and if the lock is not acquired and if it's busy, then we log the same. And finally, if the thread panics, we also handle that exception. Okay, and finally we just wait for 50 milliseconds and finally just push the handler to the handles vector. So this is the difference between mutex and rwlog. So mutex will make the lock unavailable even if a thread is reading the data, whereas rwlog, it will only freeze when there is a write operation going on, right? If multiple threads are just reading the data, then you will not be logged out. Okay, this is why rwlog is a good pattern to use when you have a lot of reads and occasional writes. Let's save this, let's run it again. Awesome. So you can see the try reader was also able to acquire the log, and because you are not writing anywhere, we did not see any conflict between these two threads. Let's clear this. Let's look at the next method, which is a write, and this is a blocking method. So we just first acquire ownership into the write log, and then we'll define the function where once we acquire the log, we're going to use the write method. What's the difference between a method and a function, you ask? So methods you can call using the dot operator, whereas associated functions you need to call using the double clone operator. Okay, so that's the difference. And methods have self or ampersand self, as in the address of self, as one of the parameter, and only then you can call it a method. Otherwise you should call it as an associated function, and that's just Rust terminology. Okay, So yeah, here we just mutate the state, and we can use the write method to acquire the mutation lock. And finally we're just writing the values, and just let's push the handler and save it, and let's run this. See, as the writer tried to mutate the value, you can see the try reader, the lock was busy, and it got locked out, because whenever like I said, whenever a thread is mutating the value, the lock will be unavailable. So this is what we saw here. Let's look at the final method, which is try write. Here, as always, we first acquire ownership using the arc clone, and then we define the writer handler function, and here we're just going to loop 8 times and use the try write method. And here we need to define all the handle cases. So first, when we acquire the lock, then we say that we succeeded the write attempt, and if we failed, then we just say the writer attempt, we couldn't acquire the lock because the lock was busy. And finally, if the thread panic, we handle that exception as well. And finally, just push the handler to the handles vector, and let's run this. We can see the try writer succeeded on attempt 1, and we got the exclamation mark immediately after the hello. So ideally you would want the exclamation mark after the word, right? Not before, not after hello. So this is one of the issues when you have multiple threads mutating the same state. You need to think about the sequence of operations very carefully, because the order is not guaranteed. So that's about it. So this is how you use RW lock, a pattern that you want to use when you have a lot of reads and occasional writes. Okay, awesome. So I marked RW lock and the corresponding methods, and also the many readers topic in green. Okay, in this section we're going to look at the next pattern, which is scoped threads. Scoped threads allow you to borrow without having to use arc primitive. The way arc works is every time a shared reference is created using arc clone, the counter is increased, and this is stored in a heap memory. So by using scoped threads, we are getting rid of this heap memory allocation. So scoped threads tend to be slightly faster and cheaper to run because you're using less memory, and this is useful when you have threads which are tightly scoped with the parent thread. Okay, I created a new file called scoped borrow, inside which I created a public demo function, and I'm going to export this as always from the mod file. And in the main.rs file, I'm going to run the scoped borrow demo. That's it. First, I'm going to import the mutex primitive and the thread module. Then I'm going to create a new state, which is just a vector of 3 values, and wrap it inside the mutex primitive. All we're going to do is add a new element to this vector and calculate the sum and just print it. Okay, so then we're going to spawn the scoped thread. So we can spawn a scoped thread by using thread and the scope associated function, and then inside that you can pass a closure which has scope as one of the parameter. Okay, and then you can use scope.spawn to spin up the thread. And in this case, I'm going to spin up 2 threads. Inside the first thread, I'm going to acquire the log and then add value 4 to the vector, and just add a println statement that the producer has pushed a new value. And then in the second thread, I'm going to calculate the sum and just print the sum. Okay, and finally I'm going to print a message in the main thread that all the threads have been executed. So the way this works is, every time you call thread scope, this is going to block the runtime until all the threads inside it are closed. So you don't have to use join or isFinished functions like we did with regular threads. Okay, so let's save this and let's run it. Awesome. As you can see, the value, the total value is 6 and a new value is pushed. Okay, and again, you must have noticed something, right? If a new value is pushed, the value should be 10, right? Not 6. So again, the sequence of threads is not necessarily guaranteed inside the scope, which is what I wanted to demonstrate in this example. So first, the second thread had run, so we calculate the sum 3 plus 2 plus 1, that is 6. That's why we see the sum as 6. And after that, the first thread had completed executing. So the value 4 was added after the sum was calculated, which is why we did not see the sum as 10. Okay, and after all the threads are closed, without having to use the join function, we get the final print line statement. That's nice. You might be thinking, can we access a log in the main thread? Yes, we can. Let's demonstrate that. So finally, I'm just going to have a final state variable where I'm going to acquire the log and print that. Let's see if that works. Awesome. You can see that the numbers after scope with the new vector. So yeah, you can acquire the log in the main thread. Now comes the next question. So if you can acquire log, can you acquire multiple logs? Well, let's see what happens. I'm going to create a new variable called final state 1 where I'll attempt to acquire the log in the main thread and also print that just like we did earlier, and let's see what happens. You can see that the program doesn't run after the first print line statement, and I really wish the compiler had thrown an error here, but unfortunately it doesn't. So you cannot have multiple logs within the same scope. That violates, how mutex works. So one thing you can do here is to call the drop function and pass final state. Then if you run it, you should be able to do this now. Awesome. So you will see 2 print line statements. So this works. The other solution is to use scope brackets so that we isolate the scope of these 3 lines. And as soon as the execution gets out of the block, the lock is released and the lock will be made accessible in the next line. So let's see how to do it. I'll just delete this line, and all I need to do is wrap this in curly braces. That's it. I'll just move these 3 lines into this one. So now we are creating an isolated scope. So as soon as we come out of the scope, the lock is dropped. So let's run it again. Awesome. So it works fine. That's it. So this is how you use scoped threads. I'm going to mark this as complete in the YAML file. That's it. Let's move on to the next pattern. In this section, we're going to look at a pattern where we have many writers appending to a log. I'm going to call it Q Mutex, and I'm going to create a public demo function which I'm going to export from the mod file. And then in the main file, I'm going to run the demo function. That's it. First, we're going to import the thread module. Then we're going to use arc and mutex. Again, we need arc and mutex to implement this. And then we're going to import vec_deque. So the difference between a vector and a vec_deque is, in a vector, whenever you push something, it is added at the end. And whenever you pop something, it is removed from the end. But the beauty of vec_deque is it gives you order of 1 time complexity for both push and pop at both ends, at both front and as well as back. Okay, so we'll have we'll have a few threads in this function where one thread will just keep adding logs using push back, and then we'll have pop front to display the logs. Okay, so first I'm going to create the log state, which is going to be wrapped inside the arc and mutex primitives like we did earlier, and instead of a vector we're going to use vec_deque. Okay, then I'm going to create the handles variable to store all the handles. Then I'm going to create 4 workers. With each worker, I'm going to get shared reference using arc clone, and then I'm going to push the handler function inside the handles vector. Okay, and inside this function, first I'm going to just format a log using the format macro, and then I'm going to get reference to the queue by using the log function on the mutex, and then I'm going to push the log entry using pushback. Like I said, vec_deque gives you order of 1 complexity for both pushing and popping data at both front and end. So in this case, we're going to append the logs at the end. Okay, then I'm going to join these handles to just wait for these threads. Okay, and then in the main thread, I'm going to get reference to the log, and I will have a while loop to log the entry every time one of the child threads, push an entry to the queue. Okay, and here we're going to use pop front so that the oldest log will be first extracted and printed. Okay, so if we were to use a vector, we would only have push and pop, but because we're using vec_deque, we can use pushback and pop front. All right, let's run this. Awesome. So we have log entries appear from the print line statement in the main thread. Okay. One thing that you notice is that I ran this function 3 times and the order is different for each invocation. So all these child threads, right? So despite, even though you're using a vec_dequeue, the order of the child thread execution is still not guaranteed. Okay. I'm going to mark this section as complete in the plant UML file. Okay. Let's move on to the next pattern. In this section, we're going to explore a new synchronization primitive, which is onceLog. So instead of wrapping the data inside mutex or read-write log, we're going to wrap it inside onceLog. And onceLog is useful when you need one-time initialization. So whenever you call get or init a function, you're going to initialize the value once, and for every subsequent call, the same data is returned. Okay. And that falls under one-time initialization and shared later pattern. Okay. This is useful if you want to initialize some global config in your project that is only initialized once and reused throughout the project across the threads. Okay. I'm going to create a new file called onceinit.rs and create a public demo function inside it. I'm also going to export that from the mod file. And in the main.rs file, I'm going to run this demo. That's it. Inside the demo function, I'm going to import the arc primitive and also the onceLog primitive. So instead of mutex, we're going to import onceLog primitive and also the thread module. And first I'm going to initialize my shared config, and like I said, instead of mutex, we're going to use onceLog new function. And then we're going to create handles to store all the thread handles, and we're going to spin up 4 threads. And inside each thread, I'm going to get the shared reference using arc clone, and then I'm going to push the handler using thread spawn. And inside the thread, we're going to first, to initialize the data, we're going to call config.get or init. That's the function we use to function or a method because it takes self as one of the parameters. So we can call this method to initialize the data. So inside this, we can pass a closure, and inside this closure, we're just going to print that this worker ID is performing initialization, and then we're going to return a string. Okay. And again, I don't have semicolon because if you want to return something from a function or a closure, just put the last line as, just leave it without semicolon, or you can say return the value and then semicolon. Okay. And then I'm going to print the value that gets assigned to the value variable. Okay. And finally, I'm just going to loop through the handles and just call the join function to wait for the threads and, just to invoke the threads. Okay. Let's save this and let's run it. Awesome. So for worker 0, we see that the data is initialized, but once the data is initialized, for subsequent calls, for worker 1 and 2, the value is directly returned. We don't see the worker performing initialization step. Okay. We have a couple of other methods that we want to explore in the onceLog primitive. So we have looked at new and get or init, but we haven't looked at set or get. Let's explore those with another example. Okay, I'm going to comment this out and duplicate the code and also uncomment the first demo. And instead of setting the value with get or init, we're going to use the get and set methods. Okay. In this new demo, first I'm going to create a scope block, and then I'm going to have the first thread where I'm going to set the value using the config.set method, and I'm just going to add if-else block to just handle exception in case the value is already set. And then in the remaining threads, I'm going to loop 20 times. And inside each loop, I'm going to try to read the value using the get function. And if we get the value, we're going to just print it using the print line statement. And we're going to wait for 50 milliseconds for each iteration. Okay. Finally, I'm just going to use handle.join on all the handlers to invoke the threads. Let's run it. When I run this, I don't see a difference when the value is set and when the value is not set. So I'll just tweak this example slightly. Instead of in the first thread, I'm going to wait for 2 seconds and then set the value. Whereas in the second thread, I'm going to handle all the cases using config.get using the match operator, so that when the value is set, you will see the value, and if it's none, you will see another message. Okay. So in the first handle, I'm going to sleep, make it wait for 2000 seconds and then set the value. Inside the remaining threads, first I'm going to wait for 100 milliseconds for each iteration. Then I'm going to wrap the config.get output of the config.get function with a match operator, which returns an option. So we just handle sum and none. When we get the result, we just print line the value. If not, if we get none, then we just say that no value found. Let's hit save. Let's run this. Awesome. So when we first run it for the first 2 seconds, we will see that the workers have found no value, both worker 1 and 2. And after 2 seconds, worker 0 set the config. Then we see worker 1 and 2, the value of lazy config. Okay, perfect. So now we have covered both the get and set methods as well. Let's move on to the next pattern. In this section, let's look at atomic usize and ordering synchronization primitives. These two are useful to implement a pattern where you have many writers for counters or flags. So you can use this pattern when you want to implement global counters where the overall aggregation matters more than the order of aggregation, and you want to implement some kind of like global metrics. Okay, I'm going to create a new file called atomiccounter.rs, inside which I'm going to create a public demo and export that through the mod file. And in the main.rs file, I'm going to run that demo. That's it. First, I'm going to import the required modules. So I'm going to import arc and thread. And instead of mutex, I'm going to import atomic usize and the ordering. Ordering is an enum, atomic usize is a mutex, and we're going to import this from the atomic module. Okay. And then I'm going to create the state that will be shared. And here we're going to wrap the state, which is 0, inside the first with using atomic usize and then using arc. Okay. Again, because this is a counter, you can only use a usize type inside it. So you cannot use strings or F32 or any other type inside the state. Then I'm going to create handles to hold all the handlers for threads. Then I'm going to create 4 workers, and inside each worker, I'm going to get a shared reference using arc clone, and then I'm going to add the function for each thread using thread.spawn. And inside this, I'm going to loop 1,000 times. And you can add. So what I'm basically doing is creating a few threads, and inside each thread, I'm going to increase the counter value a few times. Okay, so we can increase the counter value using fetch add. We can pass the value, and we can also pass the ordering. Okay, we'll get to ordering in a second. As you can see, ordering is an enum and it can hold one of these values. So we'll get to ordering shortly, but let's complete this example first. So after you add the value, after the loop, we can get the current value using shared.load. Okay, using the load function. And even for load function, you have an option to pass the ordering in, and here we pass the ordering as relaxed. And finally, we can just print the value. And then all you have to do is just wait for all the handles using handle.join, and finally print the final value in the main thread. Okay, let's hit save. And regarding the ordering, I went through the standard documentation twice, and I even created a few examples using AI, but I couldn't really tell the exact use case for ordering. But what I could understand at a high level is that on this list, right, the higher up it is, the more relaxed the the ordering type is. So let's say if you use the value of relaxed, it will have fewer runtime checks, and therefore it tends to be faster as opposed to using sequential CST, in which case there will be more number of runtime checks, and therefore this tends to be slower. But if that is the case, I actually created a loop. Instead of 1,000, I tried adding a 20 million loop for each thread, but using both relaxed and sequential CST. But even in both the cases, I didn't see any performance drop. So I couldn't really tell the difference as to why, maybe if I have a more complex loop, a more computationally expensive loop, that might make a difference. But yeah, I mean, at a high level, what I could understand is the lower the value on this hierarchy, the more performant the ordering will be, because fewer runtime checks will be performed. Okay, that's it. Let's hit save and let's run this. Awesome. As you can see, the worker 1 observed the value, worker 2, worker 3, and so on and so forth. And finally, we have the value to 4000 because each thread we are incrementing by 1000 and we have 4 threads. As you can see, the value that the worker observed is different at different stage. So like I said, this pattern is useful when you care about the final aggregated value, which is correct in this case, right? We are aggregating by 1000 in 4 threads, so the final value should be 4000. So the final value would be right, but the order of the sequence in which the updates are made might differ, which will give you a different value for each worker threads. So like I said, if you care more about the final aggregated value and not the sequence in which the aggregation is done, then this is the perfect pattern to use. Okay. So if you take a look at our UML file, we have the following methods for atomic usize. So we've looked at new, load, and also fetch, add. Let's look at fetch, sub, compare, exchange, and store. I believe these are not covered, so let's include those in our examples. I'm going to duplicate this code and comment it out so that I can include the other methods too. Fetch sub works very similar to fetch add. Instead of addition, fetch sub does subtraction. Okay, so let's do something different. Let's initialize the value to 100,000, and inside each thread, instead of adding, we're going to subtract using fetch sub with a value of 1. Okay, and let's run this. Perfect. So you can see the final value as 96,000. So 4,000 is subtracted from 100k, which gives you 96,000. And like I said, the sequence is not necessarily guaranteed. So you will see each worker observing a different value at the end of the operation because the same counter is being mutated by multiple threads. Now let's take a look at the store method. All store does is replace the value in the store with the value that we pass. Okay, so I'm going to create a new thread here, which is going to update the value after 5 seconds. The reason I added 5 seconds delays is so that we can observe the results of the previous threads. Okay, and yeah, first I'm going to get a shared reference, and then I'm going to push the function definition into the handlers. And like I said, first wait for 5 seconds and then get the previous value using counter.load method and print that value. And then we can use the store method to replace the value with 78. Okay, and then finally print that as well. And that's it. Let's hit save. Let's run this. Here are the observations from the first 4 counters, and after 5 seconds the previous value was 96,000 and then it was replaced with 78. Awesome. Finally, let's look at compare exchange. Compare exchange takes 2 values, the current and the new one, and also takes 2 orderings. And what it does is it compares whether the value that we're passing matches with the existing value and returns a result. If the value is already if the value is matching, it results okay. If not, it results an error with the previous value. So let's implement compare exchange in the second thread handler, where we wait for 5 seconds and update the value. So the last value that we set was 78. So let's implement compare exchange, where we say that the current value is 78 and we want the new value to be 100 with the ordering as relaxed. And like I said, it returns a result, so we need to handle both the cases. So in case of okay, that means it's success and we get the return value. And if the value doesn't match, if the current value that we pass does not match the existing value in the counter, then it should return an error and we should print the value here. Okay. And finally, after the compare exchange operation is performed, I want to get the value again using the load method and also print that so that we can see what the new value is. Let's run it. Wait for 5 seconds. So the last value was 78. So the compare exchange was a success because we set the current value to 78 and the new value is 100. So compare exchange will only be successful if the current value that we pass matches the existing value in the counter. Okay, and you can see the new value that is set in the counter is 100, the new value that we passed. Okay, let's duplicate this code and run it again. I want to see what happens when this operation fails. So in this case, the previous value was 100, right? So when we duplicate the code, the current value does not match the previous value. So I want to see what happens. Okay, let's run this again. So you can see the last value, the last compare exchange failed compare exchange error, the return value is 100 because the current value that's existing in the counter is 100. So the value was not modified. The value is still set to 100. Okay, that's about it. I think that wraps up atomic use size and the corresponding pattern. Like I said, I'm still confused about the ordering part of things. So maybe one of you who's watching the video can leave a comment and point me in the right direction. Let's mark these in green. That's it. Let's move on to the next pattern. In this section, let's take a look at convar. Convar stands for condition variable. And what this lets you do is make your thread wait until an event is received. This is somewhat similar to a pub sub, except this is multi-threaded. A pub sub is where the publisher sends a message and the consumer will immediately be notified when a message is received on a particular topic. So this works in a similar way. As always, I'm going to create a new file with the demo function and export it via the mod file. Then in the main.rs file, I'm going to run this demo. Okay. First, I'm going to import all the modules. So I'm going to import arc, mutex, and also convar. And I'm also going to import the thread module to spawn the threads and also duration to implement some kind of timer. First, I'm going to create the state. So you can wrap your state, which is just a Boolean value, true or false. And in the arc primitive, you can pass not just the mutex wrapping, but also the convar. So the convar goes in as an argument to the arc. Okay. And this is obviously an optional argument. And then I'm going to create the consumer. And inside the consumer, I'm going to get a shared reference using arc clone. And I'm going to create the thread. And here is how you extract the tuple. So previously in the other examples, we only received the lock from the mutex, and we can call the lock function again to receive a mutable instance. But here we extract a tuple, and then in the consumer, what we're trying to do is we're going to listen to the changes continuously and then print when the state is modified. Okay, so this is how we do it. We get the reference using the lock method, and then we're going to check continuously, and once the value is modified, we're going to print that the state change is observed. Okay, then I'm going to create the producer where we're going to change the state, and here also we're going to get the shared reference and spawn a new thread. Just wait for 50 milliseconds, and then I'm going to acquire the mutable reference and then change the value from false to true. And then I'm going to call the notify all method to notify the consumer. That's it. And finally, I'm going to call the join function to just make the threads run and hit save. Another thing that you must have noticed here is instead of creating the handles vector, I'm creating both the producer and consumer as a scope, and I can call dot join on the scope. So this is how we can also use the join function. Okay, let's run this. Awesome. As soon as the producer set the value from false to true, the consumer has observed it and also print the value to output. That's it. Let's clear this. The only difference between notify one and notify all is that notify all wakes up all the threads, whereas notify one only wakes up one thread. And same thing with wait and wait timeout. In wait timeout, you can pass an optional argument to wait for a certain time. Okay, let's mark this as complete and move on to the next topic. That's it. Finally, let's look at the last synchronization primitive, which is the barrier. And barrier allows you to implement a coordinated staged pipeline. So what I mean by a coordinated staged pipeline is when you have multiple threads and you have a task at hand, you can break down the task into different phases and make the threads wait until the work reaches a particular phase. Okay, here is an example of how that looks like. You have a shared state and you have, let's say, 3 different phases. Okay, and as the task progresses from one stage to the next stage, we can have barriers between the stages and make the threads wait until we reach that barrier. Okay, I'm going to create a new file called barrier pipeline, and inside that I'm going to create a public demo function and export this through the mod file. And in the main.rs file, I'm going to run this function. That's it. Remember this example in many readers where we try to mutate the string across multiple threads. Let's run this again. I need to change the main.rs file to make it run the many readers demo. Let's run this again. Alright, here, if you remember, we are supposed to get hello, then world, then exclamation mark, but because the threads are not synchronized, you will get hello first and then exclamation mark and then world. So in this example, let's use the same use case and see how we can use barriers to overcome the synchronization issue. Okay. First, I'm going to import all the required primitives. So we need arg, mutex, and also the barrier primitive. So we import these. Then I'm going to create a barrier. So in this barrier, we're going to have 3 phases. Okay. So we set the value to 3, and then we're going to create the state, which is just an empty string for now, and we wrap it inside the mutex and arg primitives. Okay. And then we're going to create 3 different phases. Okay. So 3 different threads. Each thread is going to handle a particular phase. Okay. And towards the end, we're also going to join those to spawn the threads. Okay. Then inside each thread, I'm going to get shared reference to both the barrier and the data. And inside the first phase, the way this works is we have 3 phases in this demo, right? So if we have 3 phases, then we have 2 barriers, right? Think about it. So the number of barriers is always, for n phases, you have n-1 barriers. Okay. If you take a look at the screenshot, this becomes evident. So the number of barriers is equal to the number of phases you have minus 1. Okay. In this demo, we have 3 barriers, right? We have 3 different phases. At each phase, we are mutating the string. We are going to push a piece of the string into the global state. So in thread 1, we're going to push hello, and in thread 2, we're going to push world, and in thread 3, we're going to push exclamation mark. Okay. And we can wait for each phase to complete by using the wait keyword. So let's see how it works. Thread 1, we're going to push hello, the string hello, into the global state, which is data. So let's do that. So we first do that, and then we're just going to print that, the phase 1 is complete. And then we just have to wait, because thread 1 doesn't do anything until phase 2, right? So we just wait. And also thread 1 doesn't do anything until phase 3. So we just call the wait function. So whatever piece of code you want a thread to handle for a particular phase, you insert that between either the wait, statements, or before or after that, depending on which portion of the task you want the thread to implement. Okay. That's about it. So similarly, if you look at the second thread, after all the phases are complete, I just want to put a print line statement that, the phase 1 has observed the pipeline completion. And if you look at phase 2, we're not going to do anything until the first phase, right? So we just wait first, and then we're going to push the string world into the global state, and we're not going to do anything in the third phase. So we just wait again. That's it. Okay. And similarly, in the third thread, we're not going to do anything in the first 2 phases. So we just wait twice. And then in the third step, we're going to push exclamation mark into the global state and finally print that final global state using the print line statement. So let's run this. Awesome. So you can see phase 1 inserted hello, and then phase 2 appended the world, and then finally phase 3 appended exclamation mark. And because we are using wait statements appropriately, we're able to synchronize the threads and make them run in the right sequence. So we see the final result as hello, and then world, and then exclamation mark. Perfect. So that is how you can implement a staged pipeline using the barrier primitive. I have marked these primitives and also the last pattern as complete. I guess that wraps up all the key patterns and primitives that we can use to implement a shared state approach in thread communication. I'm also going to mark these in green. That's it. Now that we are done with all the different patterns and primitives in the shared state approach, in the next video, we're going to look at the next approach, which is message passing, and what primitives and patterns are available in that approach. Okay. I'm going to commit these changes and push everything to GitHub so that you can access the repository. The link for the repository will be given in the description box. As always, leave your thoughts and suggestions in the comment section. And like I said, if you have any useful information regarding the ordering primitive, feel free to share it in the comment section. I'll take a closer look. But yeah, that's about it. Talk to you in the next one. Bye.